to a sustainable human presence on Mars. Please welcome your moderator, Mike Gold.
All right, who's ready to talk about Mars? Red wire on the red planet. So appreciate everyone turning out today. And what we're here to talk about is the transformation that is going to occur thanks to Starship. Previously, not only countries, large countries could be able to afford and even dream of going to Mars. And even then, Russia used to joke that there was a ghost of Mars, that they couldn't even get anything into Martian orbit. Now, with Starship, Mars is going to become much closer, much more democratized. We've seen the dramatic changes that SpaceX's launch vehicles have caused with Falcon. This is going to transform everything all over again. And what we're going to be able to do is going to be amazing, and what we're going to be able to do is beat the Chinese. But SpaceX can't do it alone. This is going to take an effort by the entire community, globally, and with the private sector. And we're here today to talk about, just here at Redwire, how we can leverage our technologies, our systems, to take advantage of this incredible opportunity. And if we talk a little bit about the different stages that we will be leveraging Starship, if we can go to the 4 stages of in transit. We're trying. So we talk about the powerful, powerful heritage of Redwire. We've got our rollout solar arrays. As I go, okay, thank you. So second only to the sun, Redwire provides more power than anyone out there. Our rollout solar arrays are powering the International Space Station as we speak. If we go back to the ROSA slide, wow, let's just go back to here is a vision of all the different things that we can do on Mars, but there are going to be several phases for it. If we go to the phase slide. First is going to be in transit. And in transit is not going to be easy or simple. How many people have read The Martian, the book Martian, or seen the movie? I was actually talking to the author of The Martian and asked him what was the most fantastical aspect. What was the part of The Martian that you wouldn't believe? And he said it was the radiation protection. The protection from radiation was most difficult. Matt Damon might have had 3 kinds of cancer before he got to Mars. So looking at that environment in transit is going to be very important. Then precursor missions as we get to the surface, the critical infrastructure, all leading to a human presence. I think SpaceX is taking a very modest, I know you don't hear SpaceX and modest too often, but in the same sentence, it's a very modest step-by-step approach, all in preparation of that historic first human landing on Mars, and we're going to talk you through each phase of that, if we go to the next slide. And this is going to begin with that in-transit phase. You're going to be hearing a little bit about the red hot chili peppers and what we can do with organics and food and to create a clean environment. And to talk to us about that today is our former Eli Lilly scientist, now chief scientist at Redwire. Let's have a round of applause for Dr. Ken Savin.
Hi, everyone. I'm Ken Savin, chief scientist at Redwire. And before I get started in talking about what we're going to do, I want to talk a little about where Mars is, what it means to go to Mars. And I've got a little visual aid. I'll be real quick about this, just so you can get a feel for it. So here's the Earth. If it's not flat, yeah, it's not flat. If this is the size of the Earth, then this is the size of the moon. It's actually kind of tiny, isn't it? I always thought it was like half the size of it. It's actually very tiny. If you were to peel the moon and slap it onto the Earth, it would be as big as Africa. That is how big the moon is. At this scale, this is how far the moon and the Earth are apart. So take that, walk over that way. Keep going. Keep going. Oh. Okay. That is how far apart they would be. And it's kind of an odd thing, but if you stand here at this globe and look at the moon, and then tonight go outside and look at the moon, they'll be the same size. That's how good this model is. This is 250,000 miles, give or take. That's about the distance to the moon. So on this scale, where is the International Space Station? Right here. It is about 3/8 of an inch off the surface, just skimming the surface. Okay? Think about all the trouble, time and money goes into just getting people and supplies to that, right there. Never mind over to there, right? So in this model, on this scale, where's Mars? Well, it's right here. So yeah, I stole this from my kids. You can imagine Ken Savin, chief scientist, sitting on a floor in his family room with a big tub of balls that I stole from my kids, with a measuring tape and a notepad and a calculator and a pen. And in walks my wife. What are you doing? It was pretty obvious, I thought. I'm measuring all these balls. She wanted me to go mow or something. Anyway, so here's Mars. So where would Mars be on this scale? Would it be at the other end of the expo? Or maybe through the hallway to the other end of the other expo? In fact, one way to Mars on this scale, you'd go out the expo, out of the building, across the street and up to the Broadmoor, that first Broadmoor building, through the little entryway, up the escalator, through the lobby, to the lake, do a circuit around the lake, and then come back, all the way back on stage. 4,250 feet, give or take. So about 8/10 of a mile on that scale. That's what we're talking about. If you were to put this little ball, Mars, out there at the full distance and try to see it, it would be hard for you to see. But at night, if you put it out there and someone shined a little flashlight on it, you would see a little red dot. And if you go outside tonight and look up at Mars, you will see a little red dot. That's what you would see. So the distances are huge, and what we're talking about now is this, trying to get a ship that we're going to build that's going to get us to Mars. And what would it look like? Now, this is what we would think. This is what a rocket ship looks like. But I'm sure you all have heard of people talking about like the water donut. We're going to build a water donut to protect us from the radiation. Why do they do that? Because you want hydrogens, you want a lot of hydrogens to help you protect yourselves against, shield yourselves against the radiation. But the reality is, it's more than that. I don't think a water donut is going to be enough. And I would recommend that in addition to the donut, we also send large tanks of hydrogen. And they would also be on the exterior as a shield for all the people on this craft, the plants, and all their food, and any other things that could be damaged by radiation. I'll talk about hydrogen later. But in addition to the shielding, and we can talk about all the different types of radiation and the different levels you'll get as you're going to Mars, part of what we're trying to do in these initial missions is understand the environment and prepare ourselves for crewed missions to Mars, survivable missions. This is a system that cannot fail. I was talking to an astronaut the other day, Andreas Morgsen, and he said, if you want to go to Mars, it's simple. You build a ship that will not fail, and then you send 2 others just like it. So when the first one starts to fail, you have pieces and parts you can drag from the others. In this case, part of the system are the people on that station or on that ship and the plants. And we're all trying to understand how do they all fit together. You can learn a lot from sending plants and understanding their biology as they're bombarded by the radiation as they go on their way. Of course, it's an unshielded system other than what they bring with them. Here on Earth, we have the electromagnetic spectrum, or the electromagnetic shell around our Earth that protects us from radiation. We have the atmosphere. And we're also standing on a very large rock that protects us from all the radiation that would come up from under us. But when you're on a ship going to Mars, you don't have any of that. So we can go to the next slide. So plants are going to be a key element of going to Mars and living on Mars ultimately and surviving it. We build systems, plant habitats, greenhouses that allow us to do those studies and ultimately produce material, produce plants for food and to clean the atmosphere, the environment of the carbon dioxide and other impurities that occur in the capsule as the astronauts are going. In addition, we're looking at other systems. We're going to talk about solar and other power systems, but there's also a need to be able to go after some of these key in situ resources. And I'm going to talk about that, but in the precursor missions, you try to figure out what is actually going to work. It is not a simple thing. We talk about gathering water from the regolith on Mars. Think about that for a second. Even if 2% of the regolith is water, how much do you have to dig up to get a gallon of water? About 400 pounds of dirt that you've got to sift through. NASA has come up with ways to get to that water, and there are other methods, and I'm going to talk about those in a moment. In addition, we've got the need to do a lot of this work, especially on these precursor missions, autonomously. So robotics is going to be a key piece of that, including AI and other systems that allow us to test out the robotics. What will actually work with the power that we have available to us. Next. So talking about robotics, it is not just the being there on Mars, it's the getting there. And part of that for us is to build a laboratory that allows us to test things along the way, again, without people on station to do that. So we've developed a robotics. This is done, for the most part, at our group in Luxembourg. And the robotics then allow us to use all the facilities that we've been generating or developing over the past couple of decades to do plant studies, cellular studies. We also are developing analytical systems like Raman spectrometers and other devices that allow us to study those systems along the way. When we get to Mars, that same laboratory will allow us to study the soil and the plants that we're growing on the planet to understand how well that's going to work. We're going to try to do all of this before we send crewed vehicles to the planet. And I think even though we have decades of knowledge and research that's been accomplished on Mars through automated systems like Curiosity, I think there's still a lot more that we have to do. So one of the things that our internal group has been talking about are the bare necessities, looking at what you really need to do to make a Mars mission survivable. That's oxygen, water, food, and shelter. So let's go through those one by one, just talk about what's available to us. So Mars's atmosphere is mostly carbon dioxide. It's very thin, but it's there. There is a device on Mars operating right now, a solar-powered electrolyzer that takes the CO2 and converts it into oxygen and carbon monoxide. And that works. It's a great system. And if you need to make oxygen, that is one of the systems you're gonna have there. You're also going to most likely take the water that you are able to get out of the ground, if that's where you're going to get it, and use that to make oxygen through electrolysis, right? You can take water and split it to make hydrogen and oxygen. And if you're smart about it, you'll collect the hydrogen. I know in The Martian, going back to that movie, it's a great movie, there was a scene where Mark Watney's talking about the problem that he has, and he says the problem is water. I would argue that the real problem is hydrogen, which is why I'm bringing hydrogen in those big tanks that I talked about. So if you look at our planet and all of what we're sitting in right now, there is a lot of hydrogen. It's all caught up in us. It's in the carpeting. It's in the water. On Mars, there is not a lot of hydrogen. Hydrogen is the key, because if you've got hydrogen, you can convert that atmosphere into water. There's an old reaction called the Sabatier reaction. I think the guy got the Nobel Prize in 1906 for that. It's a great process. It's what the space station uses right now to convert the CO2 back into water. So you take CO2, hydrogen, you mix them, you put them over a hot catalyst, and you make water and methane. And methane, you can just let it go off. If we're on Mars, we would capture it and turn it into something like kerosene or wax or some other needed material, but you need that hydrogen. It turns out, as a kind of a quirk of fate, hydrogen is the most common element in the universe. It's not even close. I think 90% of all matter in the universe is hydrogen. The next like 8% is helium, and then the last 2% is everything else. Mars is everything else with only a little bit of hydrogen. So we're going to have to bring some or get it out of the ground. Once you've got that hydrogen, though, you can do a lot of things. Like I said, you can make water. You can also make fuels from it. So how do you get the water out of the ground? I think it's a really hard thing. Just think about going into your backyard and digging a hole 3 by 3 by 3 feet, right? That is a tough job. There are other ways to get water on Mars. As it turns out, at night on Mars, the relative humidity is almost 100%. The atmosphere is very thin, so there's not a lot of water, but there's probably about as much as you would find in that Chilean desert, the Atacama Desert, very dry, but there are devices like dehumidifiers that can be installed, no moving, very few or very relatively small amount of moving parts that you can capture the water and then condense it and use it. I think there's going to be multiple different, that's what we're looking at, are multiple systems that are redundant but do things in different ways so that we kind of offset our risk. So we talked about getting oxygen, talked about water, food, we've talked about the greenhouses. They are going to be critical, not just for food production and understanding it, but the biology of plants is really in many ways not too different than our biology. And you can see things in the way plants react that will be indicative of how we have to protect ourselves or operate in order to be successful. Plants also will remove, as I said, impurities from the air. And the other piece of it is a very psychological piece, but it's important. Just being able to have some fresh lettuce or to see some greenery is important to people who are going to be in a tough environment. The last item I'm going to talk about is shelter. So the radiation environment on Mars, so right now we're in Colorado, right? We get more radiation up here because of the altitude and whatever. In a 6-month period here in Colorado Springs, you will get 2 millisieverts of radiation every 6 months. That's what you're going to get. On Mars, on the surface, every 6 months, you're going to get about 140 millisieverts of radiation. Okay, so you get 2 here, you get 140 there in 6 months. On the space station, you get about 70. So you're getting about twice as much as what the astronauts get in one cycle, 1 6-month cycle. So what do? Well, the kind of obvious thing to do is to find a lava tube. That's what they talk about on the moon, find a lava tube. I don't know if there's a lot of lava tubes right where we want them on Mars, but the thing to do is to bury yourself. And you'd have to do it in a lot of dirt. It's about 3 meters, 10 feet of dirt is what you got to pile on top of yourself. There's other benefits to doing that if you can manage it, but just think about that. That is a huge ordeal, even if you've got a tractor. So we've got to have a plan for that. How are you going to execute that? We've got to think through that. There are benefits. If you bury yourself in the dirt, you don't have to worry about the extremes in temperature change, right? On Mars, daytime, it's about 50 degrees. Nighttime, it's minus 70 degrees. That can wreak havoc on your structure. But the last thing I wanted to talk about is living in a hole in the ground. So let's say that's what we do. We dig a hole, we bury ourselves with dirt. I'm reminded of an incident that occurred back in the 80s, 1984, called the Watrous incident, which nobody remembers, but it's touched a lot of our lives in an odd way. And this guy worked at the Limerick nuclear facility in Spottstown, Pennsylvania. And one day he's walking out of the facility, he set the radiation detectors off. And everybody was totally perplexed. How could this, what happened? They checked him, who did you interact with? What did you touch? Nothing. Next day, they figured they were new radiation detectors. That must be the problem. Next day, here comes Stanley Watrous. He walks through them again. He sets it off again. So just so you know, in 1984, December 1984, when this happened, the Limerick nuclear facility was under construction. He was a construction foreman. There was no nuclear material at that facility. And he set that detector off on his way into work. So they put him back in his car, and they sent a bunch of guys to his house, and they looked at his house. His house, the radiation levels were 700 times the national safety limit for a workspace at a nuclear facility. The cancer risk in his home was the equivalent to smoking 200 packs of cigarettes a day. So they evacuated his family. and they started looking in there, and it turns out it was radon gas coming up through his basement. Now, we've heard of radon gas. You may have had a radon test in your home. Before that time, nobody even thought it was a problem. They knew of it, but is it a real thing? As it turns out, in our lifetime, of all the radiation you will be exposed to, going to the beach, sitting in front of your microwave, waiting for the burrito to finish, going getting CAT scans or dental x-rays, 40% of all the radiation you will be exposed to is radon gas. So think about it. For us, it's because we're in enclosed buildings. Some of us have basements and live in our, spend time in our basements. Think about these people. They're living in holes 24 of 25 hours a day, right? The Martian day is a little longer. They're like little hobbits in there. And if we don't think about these things, it's the little things that are going to get us. And that is one of the things that we've spent a lot of time. We're in our team, we're thinking about the little things. What is it that's going to make this work or hurt us that we haven't thought about? What is real in making this whole system work? So I think I'm done, and we'll pass it on. Yeah.
Let me just say, very glad we were talking about Mars, not Pluto. I think we would have run out of rope. And thank your kids, Ken, for the ball. And to get back to Starship, we've talked a lot about Mars sample return and bringing samples back from Mars. What Starship will enable is we can literally bring the laboratory to Mars. This is an opportunity that is unprecedented relative to bringing technology that can enable science like we haven't seen before. And as Ken describes, we have autonomous capabilities at Redwire that we've demonstrated and honed on the International Space Station. We have 11 payloads on the ISS, more than any other company in the world. We can bring that technology to bear now on Mars because of that. But we can't do anything on Mars or anywhere else without power. Power is the absolute key to be able to make anything work on Mars or anywhere else. And at Redwire, again, we're very proud to provide the power to the International Space Station via our rollout solar arrays. We provided the power for the DART mission. We are building rollout solar arrays for the power propulsion element for the Gateway that will be the largest ever deployed by humanity. And we want to be providing that power on Mars. So to discuss power, we have yet another fantastic Ken. We have many, many terrific Kens at Redwire. Ken Steele, come on up. And he is going to talk about how we will leverage Redwire's proven technology on Mars for power.
All right, so I think we're going to see him. What's that? Okay. My name is Ken Steele. I'm an SVP of Business Development here at Redwire. And I've been doing power in space for about 25 years. So I've worked on both the PV side and the structure side, and I'm happy to be here today. We're going to talk about ROSA, its capabilities, where its heritage is, and where we see it, the benefit of it in Mars. Here we go. So here's the power grid that we saw earlier today. These would be horizontal ROSAs. These deploy and retract. We have methods that we can use to remove the dust through vibration techniques and other things like that. And we're going to see ROSA deploy. So Mike talked about the International Space Station and ROSA. We've built 8 wings. These were folded and then rolled out by the astronauts on the International Space Station. And you can see this deployment here going out. This is obviously faster than typically what you'd see. This was slowly, basically deployed using EVA tools by the astronauts. The robotic arm also used to place it in the orientation right in front of the old solar arrays. These solar arrays have technology that is far better, almost 3x the conversion efficiencies of the old ones. So these smaller arrays actually generate more power than the old ones do. Again, we've put 6 of them up there. They are sustaining the International Space Station longer than anything else could remain on it. just due to the wear and tear that it's had for the past 20 plus years. Not only have we provided low Earth orbit sustained power for the habitat, but we've also done a mission to Didymus, an asteroid, to show that we could actually defend against an asteroid hitting the Earth. This was basically a kamikaze mission with our DART solar arrays. They were a little bit smaller, only about 3 kilowatts per wing versus 27 kilowatts per wing on the International Space Station, but they still have high specific power, which is a watt per kilogram, and it also has a very high stowed volume, so watts per meter cubed, to allow this mission to be successful. The mission was successful. We actually did move the trajectory of that asteroid, and so there's another demonstration of capability of the ROSA. We are building right now over 20 geosatellite solar arrays of ROSAs in our factory that have a combined total power of about 300 kilowatts. And if you think about it, to convert even the best efficient solar arrays, you need 1 meter to get 300 watts. So when you think about all the meters where we're putting up there, and ROSA is able the capability to be able to do that. So if we look at ROSA on Mars, we've done a lot of work for lunar to deploy and retract, to remove lunar regolith. It's a capability that is far surpassed in terms of its heritage for any deployable system that can retract. We did a space station experience demonstrating deploy and retract in 2007. That was successful for 3 times. We've done a variety of deploy and retract and qualification in environments that shows the demonstration capability of this product. And we've also done horizontal deployment of ROSAs for I think it was an AR4L mission. We've spent a lot of money on SIBRs and used that money to demonstrate its capability. What we see here is basically a solar farm that we would see quite a few ROSAs to basically power the grid or to power a power station. At first we're going to be doing it autonomously, where each rover platform would have its own power, but eventually we'd have a power platform that people could come up, charge their batteries, and then move on to whatever mission they want to go. And that's it. Turn it back over to Mike.
And a Steele, ladies and gentlemen, Ken Steele. So, I'm from Montana. I'm from Montana. Really happy to be in Colorado. After this week, I can go celebrate Passover with my family back in Montana. That's the only time you'll hear that sentence probably today. But having come from Montana, to settle the area, we had to learn to live off the land. And as we get to Mars, if we're not able to leverage insight to resource utilization, we're not going to be successful. And at Redwire, we're very proud to have, from Space Technology Mission Directorate at NASA, a tipping point for a system called Mason that is going to be able to sinter and work with lunar regolith to build berms, to build habitats, to literally build roads on the moon to take us to a pathway to the future. So we're very excited to take this technology that we're developing on the moon to be able to go to Mars and leverage it. And we're going to hear for a moment from Kari Abromitis, who will talk about the Mason program, as well as PNT and communications on the moon. But most important of all, the cameras. The cameras are the mission. When I was at NASA, we had to argue hard with the engineers to include visual cameras on Orion. We kept being told that there was no scientific value and you're taking up valuable mass and energy. But really, those images is how we take the world with us on these incredible journeys. And we're so proud at Redwire to have provided the cameras for Orion, to have provided the cameras on Firefly recently. We got incredible images of the moon, and we look forward to taking the world with us to Mars via this imagery. So let's have a round of applause for Kari Abromitis. We'll talk about everything from roads to PNT to cameras.
Thanks, Mike. Hi, everyone. I'm Kari Abromitis. I work in business development at Redwire. Like Mike said, a lot of my focus has been on optical payloads, electronics, and cameras. But I've also been fortunate enough to be involved in a lot of different planetary missions and technologies at Redwire. So I want to talk, like Mike introduced, about Mason. So you all see up here this rover performing some grading activities on the bottom here. So that's our render of what a flight Martian Mason would look like. And Mason consists of a couple different construction technologies, microwave sintering, compacting, and grading in particular. And it's really intended to do all the things that we will need to do on the Moon and Mars. Like Ken explained earlier, radiation is a huge concern. Covering a habitat with 3 feet of regolith, Martian regolith, is not an easy task. It's not an easy task for an astronaut with a shovel. It's not even an easy task for a robotic rover. But really, the reality is there's no camping trips on Mars, right? There's no like the Moon, 3 days there, 3 days there, 3 days on the Moon, 3 days back. It's minimum six months there. Including, in addition to the transit time. So there's not really an option to take everything with you. There's not an option to, have the shielding that you need with you. It's really something that's constrained. So we see Mason as, a really important technology to enable even initial missions to Mars, like we're talking about. Having something like this on a Starship in order to build the roads, berms, landing pads, habitat shielding that we'll need in order to be on the Martian surface. So in addition to Mason, I want to talk also briefly about comms and PNT. You'll see a very realistic line up to that very visible satellite in the sky providing some PNT at Mars. So right now, Martian comms are incredibly slow and incredibly limited. Any rovers on the surface are using other, the handful of MRO and other satellites that we have in Martian orbit as relays to trickle their comms and images and everything back to Earth to do commanding, things like that. And it's slow, right? Like these rovers are moving at a snail's pace around the surface. Every move is very planned out. There's not a lot of flexibility. And that's okay right now. That makes sense. It's appropriate. Going forward, that's not really going to be an option. We're going to have multiple assets on the Martian surface that will need to communicate with each other. There's no GPS on Mars. We'll need to have PNT and positioning. And we'll need to be able to get data back to Earth in a timely fashion, both for safety reasons, for communications, for help with operations. And so right now, none of that infrastructure exists. So when we talk about this initial infrastructure precursor mission to Mars, a really key part of that is bringing communications relays and satellites to set up that infrastructure and get it safe and ready for humans to arrive. So that's an incredibly important thing. At Redwire, we build antennas. We have a lot of the hardware that would go on those communications relays. And so that's something we're actively working on and thinking about that architecture. Next slide. So up here, you're going to see some lovely images that were all taken by Redwire cameras. The top 2 you'll see there are from the Orion 1, Artemis 1 mission. As Mike said, we had the cameras on that. And like Mike said, too, it wasn't initially thought of as necessary for that mission. But I think everyone here knows that, you don't have a picture of a bunch of sensor data on your wall. That's not why any of us grew up and wanted to go to space, is because we saw a big row of data and thought, wow, I want to be a part of that, right? We saw a picture of the moon and we it touched us and it inspired us to be here. So imaging is important in a lot of ways. It's important for science. Multispectral imaging of regolith is incredibly important to understanding the environment. Having terrain relative navigation, vision navigation, extremely important for safety and operations. But like Mike said, it's also important for all of us here who will not be at Mars, but want to know what's going on and, want to feel part of that, this expansion of humanity. So, we see imaging as super important, landing site selection, all these incredibly useful purposes, but also these very emotional purposes. And Redwire has been super successful at doing both. We provided the vision navigation system for the recent successful Blue Ghost landing. The cameras that performed hazard avoidance and successful landing on the moon. Those are the two bottom images there from that mission. And we just see that being a crucial part of this next step to Mars. And I'll hand it back to Mike.
A round of applause for Kari. The one issue I might disagree with, Kari, is we probably do have more than a few people in the audience who have pictures of Sensa data on their wall. This audience, you never know, but again.
That's fair, yeah.
Yeah, absolutely not. Thank you for that wonderful presentation. And I wanted to close by again saying, this is not SpaceX alone. This is not America alone. That going to Mars will take all of us. It will take a global community. And when I was at NASA, it was never Moon or Mars. I mean, Jim Bridenstine was a great uniter. And boy, you think, Republicans or Democrats are bad, Yankees fans, Red Sox fans, you should see those Moon-Mars people. They would really, really go at each other. So it's Moon and Mars. And as we go to Mars, we need the whole world in on this. That again, Starship provides opportunities for mass and volume like we've never seen. And it's going to allow countries that couldn't even dream of sending cargo or systems to Mars to be able to participate for the first time, bringing us so much closer, so much opportunity. So I hope that we can go out as companies, as space professionals, our space agencies to engage the world. I'm of course biased, where I hope we can leverage the Artemis Accords family of nations to do this. I do want to apologize. This is an obsolete slide. It's 54. Thank you, Bangladesh, for coming on board and adding to the Accords. But this is what we're going to need to do to be able to take advantage of this new opportunity. Redwire is a global company. We have operations in Belgium, where we're building the International Berthing and Docking Mechanism for Gateway. Luxembourg was mentioned with our robotics. We just opened up an office in Poland. I am just getting over Polish COVID. It's worse than regular COVID. You have to take a lot of pierogies. But these are countries that are just getting into space, and now because of Starship, they could literally be putting their technology and hardware on the surface of Mars. And this is how Mars is going to bring us all together. Space isn't just about better technology, it's about building a better future. So let's go all in, come together, leverage the opportunity of Starship. Let's go to Mars together to bring us closer together here on Earth. Thank you so much.